One thing you need to understand the difference between is the test statistic and the p-value. So I'm going to explain the meaning of p-values and also determine the critical values for tests. So talk about when the test statistic is significant and when it isn't. So if you remember, in the normal distribution you've got this middle red area which accounts for 95% of the distribution. So the two white tails correspond to 2.5%. So these are the strangest 2.5%. So they are 1.96 standard deviations below the mean or 1.96 standard deviations above the mean. Any result more extreme than that is really unusual and you'd think about being suspicious. So when you've devised a method for comparing your two different hypotheses, alternative to your null hypothesis, you've devised something called a test statistic. So then you can figure out when is it sufficiently strange that you no longer accept the null hypothesis, which is your mean, your red bit. When is the data so different to the null hypothesis that it falls in one of those 2.5% at either end. So that is the critical value. Those 1.96s become the critical value where you reject the null hypothesis and therefore you have to accept the alternative hypothesis. Now for a normal it's easy to explain, for other test statistics it's a bit harder to explain. For a normal distribution they're devised by what's called the Z values. So to figure out a level of confidence for your test, so you pick out how sure do you want to be about your test, and then you can figure out what the critical values are. So we already discussed this multiple times that the critical value for 95% confidence is 1.96 standard deviations. If I only wanted to be 90% sure in my test, then I could reduce this to 1.64 standard deviations. But if I wanted to be 99.9% confident, then I'd have to increase this to 3.29 standard deviations. So as we want to be more confident and more secure that we should reject the null hypothesis and that the null hypothesis is definitely wrong, we need to collect more evidence with a stronger deviation from the mean in terms of standard deviations. So sometimes when scientists are trying to find something that's particularly obscure or very important to do, they will talk about something that is 4 or 5 or even 6 standard deviations away. This gives them a confidence above 99.9% confident. So they did this, for example, with the Higgs boson. Now, p-values, like the confidence interval, has the threshold. So we set these at a 95% test means there's a 5% chance that you're going to reject the null hypothesis when it's true. Now the probability of rejecting the null hypothesis when it is true is known as the p-value. And the p-value is usually set as a threshold. You're looking for any value that's less than 0.05. Now what you can actually do is calculate where within the distribution of p-values that particular critical value, that particular value of the test thing happens. So for example, for the Z distribution, if I find a value and the test statistic is 1.96, so it's 1.96 standard deviations from the mean, then the p-value of that will be exactly 0.05. But if it was 3.26, then the p-value for that would be 0.0001. So you can calculate p-values. This is a good use of SPSS because it can calculate the p-values explicitly. When we had to use calculators, you had to work these out via a process called interpolation, which made them quite difficult to work out. Modern software allows you to get a p-value for each of the values of your test statistic. So traditionally the boundary is picked of 0.05, which means you're 95% confident that you've correctly rejected the null hypothesis. It's going to be in those tails of the curve. If the p-value is 0.001, then you're 99.9% confident that the null hypothesis should have been rejected. It's arbitrary where you pick this. In some cases you want to pick it to be higher. So for example, if you're testing for a deadly disease and you need to be absolutely sure that you found it or not, you're going to need to increase the confidence. and decrease the p-value. But if it's something more general, then we usually stick with the 0.05 value.